Good evening, one and all. Once again, welcome back to the Adult FDP on Next Gen AI training organized by the Department of Computer Science and Engineering, Rajiv Gandhi Institute of Technology, CODi. This is the third day of our FDP, and in last couple of days, we got introduced into the basics of machine learning and artificial intelligence. Then we started with the conventional machine learning techniques and later moved to the concept of neural network. Hope all of you are enjoying this FDP and enriching your knowledge in artificial intelligence and machine learning. Today's resource person is Dr. Vijay Krishna Menon, and to introduce him and to welcome him into this FDP, let me invite our HOD, Dr. Krishnan K. Thank you.
Thank you, sir. Dr. Vijay Krishna Menon is an accomplished expert in artificial intelligence and data science with 2 decades of experience in research, teaching, and complex problem solving across academia and industry. He earned a PhD in mathematical linguistics, MS in computational informatics, and MSc in software engineering, grounding his expertise in strong theoretical foundations. Dr. Menon has held academic positions, including serving as a faculty at Amrita Vishwavidyapeetham, and has also led data science initiatives in industry. He is currently the AI/ML architect at Air India's Center of Digital Innovation, where he guides the development of AI-driven solutions for the aviation sector. Thank you. Thank you very much once again. Thank you very much, Vijay, for accepting our invitation. You may start.
Yes, that was indeed an introduction, sir. Thanks a lot for that. It gives me a lot of pleasure, happiness, honor to actually have Professor Unnikrishnan actually introduce me like that, because I am his student, a proud student. But that happened like around 25 years ago. So it's been quite a long time, and nothing gives me more pressure than to, accept the invitation, from one of my gurus like this. So this is a very good moment for me too. So welcome all of you to this section where we will start with CNNs, RNNs. So the first session will be on CNN as one of our main methods that we'll be discussing today, about a lot of things about CNN. So we'll start without much delay. What I'm planning is to give you a presentation on the topic, and while we are in the presentation, we might switch back and forth with some code. So I've shared the code in the common directory, which User has posted here. So I hope you can access that from my folder. There is a folder named Dr. VKM. So you can actually go in and access the 2 code files that I've put. They are basically collab notebooks. So it's very easy to use nowadays. So you don't have to do any environmental setup and all that kind of thing. So I shall share my screen. Just give me a moment. So in the meantime, I'll just switch off my camera because of want of bandwidth. I don't want anything interfering with this thing. So if you can't hear me, please give me a message. I've opened the comment section here, so you can just put a message. Even if you have a question, you can immediately put a message there regarding what we are discussing at that point. Just a moment. Can you see my screen?
Not yet.
Just a moment, sir. I might have to, I think this, because I've opened this in a browser.
Okay. Okay.
Let me just see. Yeah, I think now it is sharing.
Yeah, it's visible now.
Wonderful. Just before we start, I will ask small favor of you. You can type in the comments, as I said, or you can just, if your mic is not disabled, I hope not, but you can just directly speak with me. The one fundamental question, because we are going to deal with a lot of deep learning today. CNN is a deep learning approach, and so is RNN and deep sequence networks. So since you have already covered traditional machine learning, and this has been around, for some time now, we've got around 20 years of deep learning now. So right from say 2005 to 2006, I would say 2006, so at least 19 years of deep learning. So that should have actually made us aware of what deep learning and machine learning is, and then what is the fundamental difference between ML and DL. So why we go for deep learning and why we still use ML when most of the deep learning results are amazingly superior than traditional ML. So what is the reason behind this? This is an essential question we should answer before we go into any details regarding deep learning architectures, including CNN or RNN or whatever, even normal MLPs, multi-layer perceptrons, which is also the fundamental deep learning network, that architecture that is there, fully connected. So can I ask this question? So I would like to know the answer to this. You can post it here. So just a small interaction before we start. I'll just post this question. What is the difference between, you can answer to this, then we'll continue with the presentation. And by the end, I will check. So then I will get different interesting answers, because this is a fundamental question. Yeah, I think I'm already getting some answers. Anyway, I'll post the question. I'm not commenting on the answers right now. I'm pretty sure some of you will nail it. This is a very, very crucial interview question. In many, many, many places, I've myself interviewed at least 50 to 60 candidates during this last 3 or 4 years. And I've asked this question to at least the alternate second candidate I've met, maybe alternatingly. So at least 30 people I've asked this question, and at least 5 of them have given me wonderful answers. But then the remaining were completely clueless what they should say. They had all different type of answers, but they didn't have that, the thing that hits on the head of the nail. Okay, what is the fundamental between DP and ML, DL and ML, sorry, deep learning and traditional machine learning? That is the idea. So pin the question there. Yes. Hold this in your mind. So we'll get back to that. Okay. Now let us continue with CNN and the yet another code story. Okay. So what generally we'll be doing today, we'll be exploring CNN building blocks, how we can build the CNN-based architectures to solve machine learning problems. So there are a typical class of problems that CNN solves. No, it is not image processing alone. There is a different class of problems that CNN typically solves. And that is what we're going to see. So don't take this at, I'm not going to have slides labeled exploring CNN, training CNN and all. I have a very different deck altogether. But this is the crux of what we will be seeing. Training techniques and modern advances in CNN, and then how CNNs relate to the real world application. So we'll see some examples and try to understand. This is the most crucial thing. Understand why, what, where about CNNs. Okay. Why we use CNNs, what CNNs actually do, and where do we apply them. Okay. On what kind of questions, what sort of problem solving. Okay, going into a bit more deep. So we have traditional ML, which you have already seen. So ML basically, from ML we have artificial neural networks, which is also an ML technique. It's not something big. Then we have deep neural networks. So as we know, deep neural networks are having a lot more parameters than traditional ML, for good or bad, because that is a question we posted. So I'm not going to comment on that. So always having too many parameters or too little parameters is not always good, right? So there are small things that needs to be small. Like if you want to repair a watch, you need smaller tools. If you want to repair bigger machine like a industry scale pump or something, you need huge tools. So it is always like that. So there is always a segregation between the small parameterized models. So when I use the term parameterized, please don't misunderstand. We'll come to that later. You can, if you have a question, you can post it there. These are confusing things. So when I say parameterized model, isn't CNN a parameterized model? Yes, it does have parameters, but we don't call it as a parameterized model. Why? Because it is a machine learning model, right? So machine learning models are seldom called as parameterized models. When we refer to parameterized models, I usually refer to very old statistical, linear regression kind of models, that were the true parameterized models, because there we actually do parameter estimation. Okay, we do parameter estimation. Of course, we can estimate parameters in multiple ways. We can do data-driven estimation. We can do sample-driven estimation. We can even do experiential estimation or even guesstimation kind of things, which are currently accepted now. But what we don't do is literally train those models, right? So that is where the difference comes. Okay, so let's get back into CNNs. So each step solves scalability challenges. What are scalability challenges? Of course, we need to scale up because our problems are scaling up. So our basic data sets that you get from markets and maybe stock exchanges. These are kind of corporate data sets. I can give you example of these because it was initially all problem solving was inside the corporate. Capitalism is a beautiful thing as far as that is concerned, because that triggered the problem solving phenomena or the frenzy, because you have to solve problems in order to make money. That is the incentive for solving problems, to solve, not just to solve problems efficiently. The more efficiently you solve, the more money you make, right? So it is a necessary evil. You need to have that kind of money driven aspect to things that literally develops that side of humanity. Okay, problem solving is no different. That also developed like that. So CNNs were essentially a class of problems that we were struggling to solve. What was that set of problems? Basically, as I said, it comes from dealing with a specific type of data. What is that data? You can see all that in the application snapshot. They're all image processing case studies, face recognition, image processing, self-driving cars, image processing, because self-driving cars need to see the road and understand what is there on the road. Medical imaging, anomaly detection, medical imaging for diagnosis. Huge impact into that. I will give you real examples. Aviation, my very own domain, but I will not say baggage scanning is something that we use CNNs particularly. We don't use CNNs at all for baggage scanning. There are even better and more accurate technologies. So we don't say baggage scanning anymore. There's no point in scanning the baggage. What is CNN going to do? Take a snapshot of the bag and then try to say whether it's a duffel bag or whether it's a suitcase kind of a bag, or it's a trolley or stroller, how do you want to call it? So that is not at all an important thing in the business. What is important is to track the baggage. This baggage actually goes through a conveyor which is like at least a kilometer long in many airports, and ends up in the hands of very, very cruel people, as far as the baggage is concerned. They literally, torture the bag, and then the bags will end up in a very cold, uncomfortable place, which is the underbelly of the aircraft, which is called the luggage hold. And then finally, what happens is sometimes these bags magically vanishes. People just keep losing bags. See, why I'm talking so much about this particular use cases, because it is my own use case. I come from the aviation industry. For the last 3 years at least, I've been in a core participant of the aviation. Even though I'm a very general domain data scientist, I work very closely with the aviation data. So I know the problems in the industry too. So that is how we are coming to this. Now, what we do, we actually put RFID tags on them. Uh, it's not feasible everywhere, not in all airports, very selective airports, at least the big ones where there is more probability of the bags being lost. How does CNN help us? Yes, CNN does help us because we are talking of at least of the order of 100,000 bags every 12 hours or so, because that depends on the scale of the the airlines as well. So without any doubt, I can say it is much bigger than 100,000. In fact, I just gave you a small number. Maybe that is not startling, considering the amount of passengers that has exponentially grown in the aviation. So how does this work? We use CNNs for a very different reason. RFIDs put on the bags will travel. These RFIDs get triggered at different locations. We know exactly where the bag has gone. So basically, that helps in tracking. There is no machine learning; it's just tracking the bag, live tracking. But then the RFID signals from other bags also get triggered. Sometimes there will be confusion within RFID signals. So we have RFID detectors that are of a very specific type, that can they also log the RFID intensity. So based on the RFID intensity, because I see we are not the only airline to use this. All the airlines, at least the most popular ones, the international ones, they do this all the time. Because now it is a need of the hour. Baggage mishandling and baggage losing is like an everyday event. People lose baggages left, right, and center. We have to track and get the baggage back to them. So for this is the only way. You have to track the baggage. How do you know that this is the right baggage that passed through that point? Because there are conflicting RFID tags. There are some other bags RFID getting triggered in our transponders. We don't know what to do. So this is called noise. Okay. So if you know RFID, then basically you can guess how this works. The frequencies are different, but again you have conflicting interference. This interference, because this RFID basically is a digital reader that directly reads the bag ID and sends it to the cloud. Okay, all processing is done in the cloud, and then there is also some image processing and all, which again is a very different kind of processing. Actually tracks the bag using YOLO kind of object detection and all. But this particular aspect is very, very important. There is a model that actually sits inside the cloud, actually going through these tag intensities which the transceiver generates. Yes, our transceivers can generate that data too, and it actually filters out noise. So this is kind of a non-image processing application of CNNs, and there is no other go-to network, other go-to solution other than CNNs here. It was a very plain and simple solution, but that actually saves a lot of money for us. Okay. Okay. Moving on. Okay. So just to recap, artificial neurons and ANNs you've already seen probably with the traditional machine learning classes. So there is one difference between ANNs and CNNs. So that I think that is coming again in the slide, but I will tell you anyway. So weighted sum plus activation output. This is what the CNNs do. So what is the weighted sum? Because we just weigh every input that is coming from every input node, and every other output node receives an input from every other input node. Now this is called a dense connection, right? Dense means you have 10 input nodes and say 20 output nodes. totally you will have around 200 connections, because every input node, all the 10 input nodes are connected to every single one of the output nodes. So totally we are saying 200 connections. So basically it's a, and then on each connection there sits a number that will multiply itself with whatever is passing through that connection, whatever data is going through that, what other number is going through that. That number is the input number. And then this weight sits on that line, multiplying itself with that number. Okay. So what actually happens is a very large matrix multiplication. So you have an input vector X, and you have a weight matrix which is 10 cross 20. That is why I said 200. And then this 10 cross 20 will multiply with this X, which is of size 10, generating a 20-dimensional vector, which is the output vector which comes out of the other this thing. And this is fed into what we call as an activation function. Activation function is like a switch. Okay, it is like basically a binary switch which decides whether to start. If the signal is very feeble, if you are getting very, very low values, then I don't want to activate. I will give you a 0. There is nothing that is going to come out of that. Okay. Otherwise, it will give you a 1 or something close to 1. That is an activation. That is good. So something significant. So in terms of voltages, it's easier to understand, right? If you are into electronics, like maybe a Zener diode, something like that. Reverse bias, it gives you low voltage. Upper bias, it gives you high voltage. So that way, kind of a switch mechanism. That is what an activation function is. Basically, this method is, this activation is necessary in order to turn the neurons off and on. Okay. So that is basically ANNs for you. But CNNs are different. CNNs are not even a network. There is no connection that you can relate to CNNs. You can only show them by, okay, a CNN is put here. There is one layer of CNN. It is one single layer. What happens in that layer? What sort of transformation? Some X vector is getting transformed to some Y vector. So let's talk of 1D CNNs first so that there is no confusion. So some X vector is getting transformed to a Y vector. So we'll get the equations maybe sometime later. So I'm going to repeat most of the stuff that I'm telling you. So that is a good way to learn. So this will, the understanding improves every time something is getting repeated. Okay, so this X vector moving to Y vector. If it is a dense network, it is just a matrix multiplication where W is the weight matrix, which is 10 cross 20. And I have a vector of size 10, 10 cross 1. So basically, what I do is X transpose W, that is 1 cross 10 into W, you get a vector of 20, 20 cross 1. That is what you get. So that is the processing, that is the computation that happens inside an MLP. What is the computation that is happening in a CNN? Okay, to understand that, we need to look further. So just to mention, keep that in mind. So it is not a fully connected network. Okay, so artificial neurons are, CNNs are not. Okay, they are not dense. That is good in a way because it lowers the number of parameters, namely the weights. So instead of having 200 weights, you need to have an order of magnitude lesser number of weights, but still you can do a very effective transformation of data that churns the information even more. Okay, that is the idea. So challenges with images. So of course CNNs were kind of discovered, or rather I should say invented. CNN, the network was invented. The method always was there. Filter design and all. Convolution is a very, very old trick in the book. Okay, very old textbooks speak of convolution, filter design, and nobody does that nowadays because it's all automated. It's all AI. So, but still, it's a very good science to understand. So we all started like that. I was basically core computer science. We never had a DSP paper also. I had to learn DSP, after that in order to understand all sorts of data. So to become a data scientist, you need to understand what data is. So this was absolutely necessary. Signal data, signal processing, and digital signal processing, absolutely necessary. Without which you can't become a data scientist. Most of that techniques we use in ML2. Okay, so the idea is noise and haze. So we can throw away a noise and haze. They're not entirely same, but people actually treat them interchangeably sometimes. But that's not true. Haze is not always noise. Haze is not noise is doesn't have any basically they're random, Gaussian random. Okay, what we call as white noise. Haze is not white noise. Haze can be colored. So it's even more difficult to remove haze unless you understand the pattern or the model behind the haze. So there is some model sitting secretly and putting this output, this patterned output onto your data that makes your data of low quality. Okay, that is what haze is. That is how I separate them. So come to that again. So too many parameters, millions per image. Of course, the image size is huge. So one full HD image, it is 1024 cross 768. How many pixels? So every pixel is a parameter. Every pixel is not a parameter. It's basically part of data. So if you want to actually pass it through a dense network, you need as much parameters, because every data number will have one weight number, right? One parameter. So imagine. So that is the way we see it. Translation sensitivity. The problem is images are not invariant to even the smallest or slightest of translations. What sort of translation? Rotation, skewing, then pulling and pushing, like what you call as aspect ratio change. You make it fatter, you make it skinnier. That kind of translations. Basically, they are transformations. So you can transform the image in any ways. Human being is able to identify the same image. Even if I give my same photo, identical photo in 45-degree angle and 90-degree angle, I'll be able to say that, yeah, this is my image. Or someone else who sees me will be able to say it. But the machine will struggle. Why? Because of the translation sensitivity. Because all the pixels, the order of pixels, the pattern in the pixels get shuffled big time. So that is a problem. So we need to address that. So that we need some method that is insensitive to translation. We call it translation invariance. Okay. Coming to further intuition for CNN. Local connectivity. Yes. So what is local connectivity? So it, as far as I just mentioned, very large number of parameters can be reduced if you understand the actual physics of the data. So in the case of an image has what we call as locality. Image doesn't change very quickly. Things don't, that kind of image is there, but that is called static. Okay. The thing that you used to see on TVs olden days, when you don't have any signal, you see static. That image is completely random. So the 2 pixels close by has absolutely no correlation. But in general terms, they are extremely correlated if they have an valid image, an image that we can see, appreciate, and understand, image that conveys information. It will definitely have that locality. Okay, so locality is the killing zeal here. Okay, the killing zeal is locality for CNN. So it makes sense that we need something that actually preserves this locality, makes use that takes advantage of the locality, and not just take all the whole data, try to find patterns with all permutations and combinations. No, that's senseless. So CNNs are efficient because of that. Shared weights. So one filter, it slides across. So because the locality is a pattern that is not going to change within an image. If you see the top corner and the bottom corner of if the same image, it is the same image, it will have pretty much the same type of locality. The locality or the correlation, when you say you move like 10 centimeters across the image, what is the drop in pixel correlation? That is not going to change. It is not just local, it is also locally local. Okay, so that is what we call a structure of the image. Okay, this is called preserving structure. So the structure is a very important thing as far as image processing is concerned. So people who worked in image processing kind of understands what the structure is. It is that drop in correlation. Maybe I'm not giving you the textbook definitions, because I'm not an image processing expert by any means of that term. This is just common knowledge of a data scientist who also works with images a lot. Okay, so I'm not giving you the textbook definitions here. I'm just trying to give the common sense perspective. Everything is common sense, so it's easier for us to understand and appreciate. So we can convey this better to our students too. So I do this all the time. When I used to teach, I used to do this common sense thing with students too. It has a lot of it. Then I ask them to go read and correlate that with the the physics given in the textbook. Okay, So this is structure is basically a thing in image processing. So preserving structure is very important for any kind of image processing algorithm, or you have to take advantage of that structure too. So CNNs do that. It's ideal for image processing. I'm just trying to prove the reinvent the wheel. This is already known to everybody, but I'm just trying to justify. These are the intuitions for CNN. Then basically it is biologically inspired. Everyone knows human visual cortex, all that things is very, very popular. Hierarchy. Hierarchy will come to that. I don't want to, I just want to mention it here, but hierarchy is a biological thing, and CNNs also do the same. We'll see what hierarchy is. CNN versus ANN, we just had this discussion. Okay. So dense, parameter heavy, and no spatial context. CNNs are spatially aware. What is spatially aware? It preserves locality. It knows where and how the image is. What is where? Okay, it knows that. It becomes spatially aware. And then they are sparse, so very easy to train, very quickly trainable, very less computation to train, and cost effective. Shared weights. One single filter designed to slide across the image can actually create one uh, entire feature. It can get a pool of features for the image with just one set of one kernel, as we call it. It's just one matrix, weight matrix, which we call as a filter. Understand basic 1D convolution. I'm sure everybody knows it, but nonetheless, I just put it here because if there are people like me, in the with the audience, if you had shown me this slide when I was actually doing my MS, I wouldn't have understood this. Without this slide, I wouldn't have understood what is convolution in the first place, because it's not something we do. I told you I never had a DSP paper. So filter design, we don't know what it is. So we don't use convolution. Maybe we've used the processing, but the sense of the term, we don't do it. So convolution is a technique to get the gist of data. So basically, why we do this convolution? It's basically easy to explain this in terms of signal. So you have an incoming signal. So what we do is we put filters on the signal to process the signal. Signal processing is all about dealing with different filters. So you design a filter so that you can mine out necessary information from that signal. Okay, like basic signals, basic filters can be like a high pass and low pass filter. I'm sure this term is very reminiscent and nostalgic because most of you have done this DSP paper. So what is a high pass filter? It allows higher frequencies to pass. It doesn't allow lower frequencies. So low pass filter, vice versa. So we can actually design the filter coefficients in such a way. The filter coefficient is nothing but a vector that sits on one side of the input. So your signal is also a huge array. It's an array of numbers. Basically, that is what a signal is. If you look at the time domain, it is just an array of numbers. Now, how do you do convolution? How do you apply this filter onto that signal so that the signal can pass through the filter and then become filtered, or in the form that we want. Like we don't want any high spike, so we do a low pass filter. So it will not allow spiking behavior, like high peaks in the signal, shrieking things to actually pass through this thing, and you get a smoother low frequency wave. Okay, that is what signal filtering is all about. How does that happen? So it is actually shown how the multiplications. Basically, we are taking a dot product. So you take this 3 1 minus 1 1, that is called the kernel, or which is called the filter, or the filter coefficients. Put it on top of, which is that black box you can see 151. So if you put it on top of that, you can take a dot product between them. So that is 1 into 1 minus 5 into 1 and 1 into 1 again. So if you add up all this, it will be 1 plus 1 minus 5. And that is how you get minus 3 in the first place. That is the first coefficient, first output of the filtered signal that you're getting. Okay. So the next, then what happens is this filter is going to slide by 1. That window, the black window, is going to slide towards the right. And then you get 5 1 4. So overlay that on 1 minus 1 and 1. 5 1 4. If you multiply, you get 5 then you get -1, and then you get 4. If you add up, you get 5 plus 4 is 9, -1 is 8. And that is how these numbers are getting filled up, you see. So this sliding process generates the vector on the right hand side. Now the problem is, our original signal was actually of size 5, but our resultant convolved signal is only 3. So we lost some information there. Okay. So this is a lossy filtering. We don't want that filtering. So what we do is pad. We put 0 on either side, and then what happens? Magically, we get a normal signal. We get a signal that is of size 5. Okay. So this filter is doing this job to the signal. It's basically filtering, as much as I can see, it is filtering lower values. Unless you have very low neighborhoods, it doesn't allow lower values to come, right? No, I'm wrong. It doesn't do that. It does something else. So we don't know what these things are. It was not a design filter. So it's difficult to assume what it is actually doing. So this is the part in the explainability of things. So when you actually put a filter and do, unless you design that filter to, exactly what was your end goal, that the signal should be like this, or it is for certain frequencies or certain types of behaviors, certain types of, envelopes to pass through, we are not going to understand what the actual thing is. You can only observe the result and then come up with reasonings. Okay, so it is not completely explainable, just like embeddings. Most of the AI nowadays are not explainable. So we do a lot to keep it explainable. Otherwise, it's very difficult to use AI practically. Because once this falters, AI cannot be trusted as of now. It works nicely at times. It also has that wow factor, but it cannot be trusted. If it fails, we are responsible for it, and we should be able to say why it has failed. So if you can't explain how it is working, how will you say why it has failed? That is the concept of explainability. So this is very, very important, that some of the things we do here should be explainable. Yeah, that apart. So that problem is there when you go to deep learning 2. We'll come to that. How we can make it explainable is also there. Okay, now CNN. So convolution as a transformation. So basically what it does, it's basically filtering, right? It's basically putting a kind of Polaroid on top of the image and looking at the image. So whatever things the Polaroid can pick, the Polaroid will send across, and whatever things the Polaroid cannot pick, it will not come across. So the resultant image. Just a moment. Just a moment. I'll be right back. So I hope you can see. 1 minute. Can you see the screen now?
No.
No.
Just give me a moment. I'll be right back. Just less than a minute. Okay. Sorry about this. Yeah, sorry about that. I'll just share the screen again. Yeah. So going forward, we were saying about the kernel and filtering. So the kernel is basically a filter. So that is how we call it. It's called a kernel. It's basically like a matrix. So how does CNNs do it? So here there is no predefined design of the filter. No design. The filter learns by itself. Okay. As with any deep learning, how does that happen? It happens through back propagation. Okay, so we train the filter. So here is where the training comes. So basically, the CNN behaves like a network, even though it is not. So we have a means to actually figure out what we want. We know what we want, and then we'll just first choose a random filter and try to work it out. That is called forward pass. And then this forward pass will give us some junk. I mean, it'll be completely something that we are not looking forward to. We know what we want, so it did not give you what you want. So then the system will compute the difference between what was given and what we want, which is called the loss. And this loss is pumped back into the system in the form of a gradient. Okay, and this gradient can go back to the place. So this can be very long, not just one layer. You can have layers and layers of CNNs alternating with pooling layers, alternating with dropout layers. So many things are stacked into a single network. So how does what happens at the end of the network? We might know only the last value, what we want at the end, probably a class. Okay, a given image, I know it is this class. I am expecting it to say class number 4, but instead of 4, you got 2 or maybe 10. So then that difference is projected backwards. So it goes through all these channels, and finally, so right now we are trying to figure out the first level filters. So how does the first level filters work? Yeah, the filter actually gets this so-called gradient, which we also call as error. It's basically the error in the prediction. So this filter had so much error in its prediction. This is not. So that error, we can use a fraction of that error to update our filters. So we know exactly how to update it. We add values to the filter coefficients inside that W, whatever that kernel matrix is, that matrix is updated with the gradients, with the fraction, with the some linear combination or a fraction of this gradient. The fraction is taken. How do you know what fraction? That fraction also has a name. It is called the learning rate. So like in any machine learning, it's the same terminology that we use here too. So that learning rate comes, it gives you the filter, and finally, the filter is updated. Again, we check whether it is working. If it is not, again update. If it is working, leave it alone. So this is the process that continues, and that is how the kernel gets designed. So because in convolution, usually the application of convolution is in filter design, as I told you. It's called filter design because we make that filter by hand. It's a handmade filter. Because the guy who processes the signal is an expert, and he knows exactly what he wants. He knows the frequencies that he wants to filter out. So using that, he can actually design either using some fancy algorithms, or maybe like wavelet transform or something like that. He can design a filter, and that filter is also like a signal, a piece of a signal that goes and sits, creates an interference purposefully, and then transforms your signal into what you actually want. Same thing here, but except that we don't design it beforehand. It is completely learned from data-driven process called training, using an automated learning mechanism called as backpropagation, which has done wonders to this world. Almost all of AI is using backpropagation. Okay, now, so visualizing filters. So how do you visualize filters? What is the whole concept of visualizing filters is, there are different. So this is also part of the hierarchy that I'm talking about. So low level, the filter actually sees edges and corners, okay, within your image. So pretty much all these examples are from image processing. I'm not giving you any non-image processing examples because this is easy to understand. It's the same concept, but images, it is more explainable. So we are taking that example, okay. So please don't get the idea that this is exclusively for image processing. Absolutely not. That is what the point I'm trying to make. Most of the applications I've used is all non-image processing. I've got a paper where I've used CNNs, a sliding window CNN approach, competing with the LSTMs or RNNs, which you are going to see later. And that is a huge, update. It was an update at that time. People thought that they can predict financial time series like stock markets and all. using LLNs, LSTMs and RNNs. But of course, they were wrong. CNNs actually did a much better job. Only thing is that you should understand the market dynamics a little bit, that you have to pump in terms of the making of that windows. That's not a fully automated process. LSTMs can, if you have enough data, you can train it and automate that process. But the data is too chaotic for LSTMs to zero in on anything. So we can use our experience to actually form the windows and then use a CNN to filter out the noise so that it gives you a better prediction. So I've got a paper on this. I'll show you the paper towards the end in both cases. Okay. So that is the idea. So low level, filters which are trained to see low level entities within your image. These are actual objects, part of the structure of the image, edges, corners. Then the next thing is textures, patterns, like skin, eyes. Eyes are glossy, right? That is the right term. Skin is kind of a matte finish, oily but a kind of matte finished. Your head will be hairy and almost completely matte finished. So this kind of thing, that pattern, so it can actually locate regions. Mid-level is basically regions, and high level are actual organelles. If you are talking of face recognition, think of the boundaries of your eyes, nose, and mouth, and everything. And then at the next level, it actually identifies these. It knows how to combine these edges that the previous layer has found, and to combine them in a way to make sense out of organs. And then the final layer is to put together these organs, understand the gapping between, like the gap between your two eyes or your eyebrows, the height of your nose from your upper lip, all that kind of thing. It is learning. Okay, all this magically goes into those numbers. All you need to do is show a photo, or maybe multiple photos, so it automatically remembers all this stuff, and then that is how it is able to recall. So all levels, hierarchically, it is learning. That is the idea of how filters visualize. So this is something that even we do. Okay, even though we might not be aware of it, but this is exactly how part of our brain works. We actually see a person, we recognize him with his features. What sort of features? This sort of features. Mainly our features are hierarchical. We don't do low level and mid level. Our at least what we are aware of are the hierarchical ones. Low level, maybe our brain is doing it without our knowledge. I'm sorry, the moment I touch it, it is changing. Okay, so then we have what is called this padding and stride. So I told you what padding is. Just go back. Padding is putting zero so that the target outcome is the same size as your input. Okay, that is important. Otherwise, there will be loss of information. Okay, so that is called padding. And what is stride? Stride is how much you are moving the filter. So I have a choice. You can actually make that in that way too. Only thing, you'll have to pad it even more. So in order to get a lossless thing. But what happens in stride is stride decides how much you have to slide that window by. The convolution filter, convolving filter, how much you have to slide that kernel by. Now here we have actually slid it by just one cell, one box, one number. You can choose to slid it by 2 numbers or 3 numbers. That is called stride. The higher your stride, the lesser will be your output. So basically you are like throwing away. So to understand this, I have a beautiful image in the next slide. Probably you've just seen the glimpse of it. I'll explain with that. So just hold on about stride in your mind. Okay, that is jumping in between. Okay, so let's go to pooling layers. So max pooling. So max pooling is like, it is not same as stride, but it also does downsampling of your picture. Basically, it does a filtering of your information. So you have a lot of information, lot of numbers in and around a portion of your region of your image. We call it region of interest. So if you look at the region, there are a lot of information, but I don't want all that information. I just want what is dominant. That is why we do max pooling. So max pooling is also, by looking at the kernel. So it has a kernel, but it doesn't do that what the CNN kernel does. Max pooling is an entirely different layer, but to make sense out of CNN, we need both. So this max pooling, how it works is, that actually comes in the next slide, but I'll just mention. It reduces dimension, so it just picks the dominant thing and then only remembers that. So that essentially downsizes your sample, your data. And finally, activation functions. I already told you what activations do. So we choose this ReLU for a reason. This rectilinear, activator, um, rectified linear activator. That is what ReLU actually means, right? So basically, it's a max function. So it doesn't have any negative values, and it just keeps climbing. It's like a 45-degree line on a Cartesian coordinate. So that is how that function looks like. Why it is like that? Because it is differentiable at every point. Because in order for our backpropagation to work, you need to take the differential of your activation point. You need the first derivative. You need the rate of change of your activation with respect to the input to propagate the error backwards. So for forward pass, you use the activator function itself, but to propagate it backwards, you're taking the gradient. And for that gradient, you have to differentiate this function. So at every node, you're going to differentiate the activation function. So ReLU is easy to differentiate because it's just a constant value. If you differentiate the max function, it's just linear. It's extremely linear once it is positive. It never gives you a negative activation, so no confusion. Activation is either 0 or positive. Okay. But there are others too. You have sigmoid, tanh, leaky ReLU, and all that kind of thing. Leaky ReLU is having some negative value too. Sigmoid is basically the S-shaped function. We also call it the logistic function. Okay, that is the sigmoid. Tanh is similar to sigmoid, but tanh has sigmoid is doesn't go negative. Okay, it goes 0 and then it goes high. But tanh actually crosses the origin and goes to the negative quadrant. Okay, shape is pretty much the same, slightly different. That's all. Tanh is not differentiable for very high values, same as sigmoid, because they almost become asymptotic to x-axis and the derivative vanishes. So that is why we don't use that a lot in deep learning. So instead, they actually invented ReLU, which is easier to differentiate and convergence is faster. Training gets affected because if the derivative vanishes, then that batch, that training on that particular batch is completely done. You get a 0 gradient and your weights don't move. It's not going to get updated. You lose the gradient. This is max pooling. So max pooling, you can see that the blue square, it chooses 9 because it's max of 4 to 2 to 4 9. So it goes with 9. This is what max pooling does. Now, how does that retain information? Is it lossy? Yes, it is lossy, but it retains the pattern. So that is exactly shown in the GIF that you can see below. This is a very famous forward you would have seen. There's a dog picture. Actually, it goes further. The full video is here. I'll share the slide. You have the video in this. I'm not going to play it in want of time. It's almost 7 o'clock. So we'll just quickly go through this and then get to our code base. Okay. So fully connected connection and layering. Fully connected? No, it is not fully connected. So flat. Sorry, I think there is a small mistake in this. Okay, that part is a mistake. So let's start with the softmax and output. So basically, this actually talks of logits. Logits are basically, what we call as, for if you know what is cross entropy, it is a kind of optimizer that we use for classification problems. CNN actually uses that because most of the problems we use CNN for our image classification kind of problems, right? So it converts logits into probabilities. That is actually seen as one of the useful things in CNN. I'll just leave it at that. You can go search this out. This is a bit more higher concept. So you can search why CNNs are taught to convert logits into what are logits, what are how it converts into probability. You can just search and see. Okay, this is all internal things about very, very deep internal things about CNN. That is why I left the first part which says fully connected, flattened features classification and all. So this is not there. That actually it should be the opposite. I don't know how that came there. My bad. But then the rest of the things is correct. So the forward pass walkthrough. Now I've got an example of how this actually does and how finally the softmax classifier is met. So the last layer of any deep learning is basically the same softmax classifier. Softmax is a standard function which basically does the classification, decision boundary classification, like in SVM. Okay, it does the same thing, right? So that is what it does.
Ha, howda?
Yeah, hello. I heard someone. So I
I
thought,
think it was a noise. You can continue.
oh, okay, sorry. Yeah, thank you. Okay, so parameter sharing efficiency, it's huge here. It's very, very big because you see, that is why we are taking the example of an image. So this, I already told you again, this is a repeat of that. Imagine the image is 1000 cross 1000. Imagine how much parameters will be there for a dense network to train. CNNs hardly will have this 1000 cross 1000 will have a kernel which is of size 7. Probably it will have 10 kernels like that. What, 70? That's it. 70 parameters instead of 1000 cross 1000 parameters. So this is the difference. And it trains like this in a jiffy. It's amazing at training. On the contrary, the next thing that we're going to see, RNNs and LSTMs, they really, really are lazy trainers. They take a long time because the computation is too dense. They take a long time because that is going to be the opposite of CNN, at least in terms of training. Okay, so gradient chain rule applied by layer, that is coming up. So I think I can show you in a real thing. Okay, so the loss functions, what are the loss functions we use in CNNs? Basically the cross entropy, which is minus log of your prediction, y cap, whatever output it is given. That is called cross entropy loss. Okay, or you can go for the mean squared error. Mean squared error is a standard thing that we do. So the derivation I have done is basically using mean squared error. So we'll see, we'll take a sneak peek into the math also to understand it better. Regularization is very, very important. Every time you do regression, you have that error, right? That is called regularization. That generalizes your model. Otherwise, your model will overfit. Okay. So even in deep learning, that is very, very, very important. But how does deep learning do that? How does CNNs do that? This is general for all deep learning, not just for CNNs. We have what is called as a dropout. Patch normalization and all are separate techniques. But within the network, how do you introduce that epsilon in your regression? Basically, every deep learning network does regression. Okay, blanket statement I'm telling you. Every deep learning network is one or the other form of regression. Even classification is regression, except that you are mapping some x to y, except that y is very, very sparse. So the cases where y is a huge set, y is not sparse, it's a denser and denser set that every x has a unique y, then it becomes complete regression. But when it becomes like you have like 10,000 x's, but you have only 4 y's, it becomes classification. Idea is you're mapping x to y, and that is regression. End of the story. It's a blanket statement I'm telling you. Every deep learning network endeavors to do the same. So let's actually talk of regularization, which is what every regression requires, that epsilon. So how does that happen in deep learning networks? By using dropout. Okay, dropout is something that Google invented. Literally, Google patented dropout, and they said no, dropout will not be available in other this thing. But finally, they did not go through with suing people, and they eventually opened the patent to everybody, even to the open the free like caffeine and PyTorch and all that guys who are still using dropout as, because they published the algorithm long back. They don't have an algorithmic patent, but they do have a usage patent, I think. So that you can go check out. This is an interesting story. How dropout, what is dropout? Something that you can tell students and impress them. So there is an entire story behind dropout. What dropout does is it will randomly select a few numbers and do not update them. That is what dropout does. And how dropout affects ANNs, normal dense layers, and CNNs are completely different. So in CNN, how dropout works is it randomly skips updating certain filters, certain kernels, or partly certain kernels. It doesn't update them. Why it wants to do that is it wants to stop that bias from setting in. Okay, it wants to introduce some randomness. So every time, see, you want to have order, you want to arrange, say something, you give it a shake, right? So dropout is like shaking the platter. You shake it. Sometimes it comes to the right order, but otherwise it might get entangled somewhere. And then how many other times you try to order it, the basic pattern is not changing. You end up doing the same thing again and again and again. The moment you randomize it or give it a shake, you will be able to order it properly. So same thing applies to machine learning, especially to neural networks. um, the neurons close by tend to learn the same thing, like redundant. So because they have common, the input is common, the weights are initially randomized. Sometimes some updates will make the weights same on multiple connections. We want each and every connection to be unique and different. Only then the effectiveness of the network comes out. Only then effectively it can read the information out of data. Information filtering is what networks do. So to enable that, we need to stop. We, instead of regularly updating, we randomly choose some 50% of the nodes to update, 50% of the filters to update. The remaining we just stop from updating. So only 50% gets updated in one batch, and the remaining will get stopped. And then another epoch, it will again repeat, pick a completely random batch again. So last time what not did not get updated will get updated now. So what happens is they'll start moving apart, and they'll start getting specialized with the pattern of data. Okay, that is called regularization. Absolutely necessary. If you don't put proper dropout layers in your architecture, you cannot. It might not converge properly. You'll get a very large. It will stop, get stagnant with a large loss, and you'll not have any accuracy. Okay. So what are the types of optimizers we use? Stochastic gradient descent. So these are the selections that you have in if you are using Keras or PyTorch and you're using the CNN con2D layer. Okay, it's not called a CNN layer, it's called a the convolution 2D convolution, basically image convolution. So what we saw here, just imagine that being happening in 2D. That is where we're going. Okay, so this is basically the math behind the update. You can see how the output, so this is Y is the output of the jth node coming out of the jth layer from the ith layer. Okay, the input is from the ith layer and you get a Y from the jth layer. So the input X is provided. Okay, and N is basically the number of samples. C, so C is basically the channel count. So basically if you're dealing with images, you have multiple channels. Images, grayscale has only one channel because it's basically black and white, and only one single pixel in the scale of 0 to 255 can indicate the amount of grayness or information. That is how it goes. That is called grayscale. But if not, it will be RGB. So there will be a separate scale for R, G, and B. There will be 3 pixels, not one. At every point, there are 3 pixels in that image. So that is what we call as channel. There is a red channel, a blue channel, and a green channel. Even if you go further, we have now satellite images are multispectral. They're not even RGB. They have spectrums, ultraviolet and infrared spectrums too. So typical multispectral, what we call as hyperspectral image has around 220 bands of channels. 220 bands, 220. That is how complex that image is. That is how the satellites are taking. So it has ability to capture data using different spectra. So that is recorded. Okay, so these are channels. So basically, just a snapshot. You don't need to understand this. Basically, this is the weights, which is a filter. This shows convolution. So it is repeating over the width W, the height H, W minus 1, H minus 1, and for all channels. So the summation will happen across the entire image, and that is how the Y is generated. Okay. So this is one full sweep of the this thing shown here, and BK is basically the filter, the bias for the kth filter, which is W. K is the filter that we are using. The other filters, K is the counter for the filter. Okay, then basically the loss, you can see L is equal to Y1 cap minus Y2. That is called the mean squared loss. You take average over N, and that is the loss. You differentiate that. So what you want is, this is called the so for the loss to be minimum, you need to have the differential is equal to, because this is a parabola, you're trying to find that bottom curving point of the parabola where you can put a tangent. So that point, you want to find the y, the values of w's at that point. So directly w's are not available for L because L is a function of y. So y is a function of w, and then henceforth you have to backpropagate and find out how much L will change when you change W. So you have to change W by that amount. So the second one, the B, gradient with respect to filters. So both W and B. B is also a bias, it is also a parameter. So both B and W, these partial differentials dictate how much you have to change the W so that your loss will be minimal. You have to bring down the loss further. So eventually the loss doesn't change, so the gradient will be 0. And you can stop the training. Okay, gradient will be stagnant, it doesn't change from time to time, you can stop. That is how training happens. That is the idea. Now you see the hierarchical visualization, which I told you. Layer 1, all edges, all lines you can see. This is the layer 1 output of a convolved image. Each this thing is basically done by one filter. So there are how many filters? 1, 2, maybe 5, 10, I think 15 filters. So this is 2 cross 15. That is a conv layer which has 15 30 filters basically. That is you are getting 30 different image snippets. Each snippet is generated by one convolution filter. Okay, so one image is split into 30 different filters, and then that is again convolved. So this 30, the next convolution layer learns to put these lines in context and build actual features like eyes, nose, ears, mouth, teeth, etc. Okay, so it is learning to put together stuff and then identify different organs on your face. And the third one actually puts the organs together and pretty much recreates the face. That is the third layer. So this is how they learn. This is their understanding. This is how they visualize stuff. And that is why we put more than one layer of CNN for this hierarchical learning. Okay, so anything as complex as a human face has to be learned in this hierarchy. And this is how the learning happens. This is why we call it hierarchical. So this is a hierarchical visualization. This is basically a level-wise visualization which I just showed you. So it's the same thing, but at a different level. This is a real case. Basically, the feature gets all the So what you can see in the last picture. Can I zoom that and see maybe? Yeah, so you can see these are parts of the car. The picture was a car, and each of these image gives you one specific part of the car, and that allows the so parallelly it is going and finding understanding each part. So even if there is any translation, a change or the orientation of the shape of the car, not in that way, slight changes. See, CNN cannot do one thing that we will discuss at the end. But what CNNs can do is on the face, if I jumble up, see if it is already trained on my face, I take my picture, jumble up my eyes with my lips and my other eyes with my nose, it will still be able to find out that it is me. Okay, it will still be able to. That is called translation invariant. I told you, translation is a problem in images because the moment you change, the data completely changes, and normal data-driven algorithms are incapable of understanding that, okay, this is the same thing. But CNNs are invariant to translation. So that kind of spatial translation where you drag the eyes of a person and keep it in his mouth position and mouth to the eyes position, still it will be able to recognize. If you don't change the features, you're just cutting and pasting, it will still recognize that image as the same person. Okay, there might be some error. It might say, yes, this is wrong, it's not a person and all. There might be other filters that recognizes tampered images. But the CNN that is supposed to recognize that it is the same person will definitely give a positive reply. It will recognize. Okay, that is called translation variant. That is why CNNs are so popular. It has been a breakthrough because of that, which we were not able to crack with normal machine learning. So this is an animation that shows the kernel. So you can see in the first input, he's dragging that small matrix, that small cursor, which is basically your kernel matrix. An equivalent output is shown on the right hand side. Okay, equivalent output of what that kernel gave you. So this is a filter that basically filtered out all the high value pixels, the black colors, the shades. It simply filtered out all the shadows. Okay, so anything that is non-shadow is highlighted. So it's easier for the machine to understand this. It's easier for us to create features out of this. More identifiable. Shadows are gone. So a picture that has a lot of shadows which are not very intelligible can be put through this filter, and you can see that it magically vanishes. You get something which you couldn't see initially is now visible. Okay, this is the idea of convolution. This is a very popular animation created by Adriya Karpathy. Everyone knows Adriya Karpathy. If you don't know, please refer. He's one of the earliest researchers in deep learning, mostly one of the pioneers of deep learning, if you want to call him that. He's a student of the co-founder of Coursera, Andrew Nag. So Adriya Karpathy is very famous even now. He's contributing even more. Now he's also the father of vibe coding. If you're not familiar with vibe coding, I suggest that also you go check out, where you can actually prompt and it will build an entire application for you. But the prompt should be clear and neat, and you can get the machine to actually do your bidding. You don't have to sit and develop the front end. Basically, for front end, it is very useful. You can make websites with that. You don't need to use Streamlit or that kind of platforms for your POC testings. We do that a lot. Go to lovable.com or Replete. These are very famous sites. They are free too. You can directly prompt and it will give you the TypeScript for the vibe code. The project, you can download the project into your VS Code and then edit it, and then it becomes a real project. You can deploy it. Wonderful. So he's very famous. You can see how the convolution is working here. This is how that flow goes. This is exactly what happens in CNN. You can see more than one filter, maybe for red, green, and blue. And then the bias is also there. And finally, the output. Output is smaller than the original image. That is expected. He's not showing any max pooling here, but that also will come. So these are some example architectures. I'll share this PPT with you. You can go check this out. These are all pre-trained things which we use for our day-to-day. Nobody trains a CNN from scratch, especially when you have to deal with large images, because it's impossible to train it. You need a lot of money. You need to probably subscribe to one of the heftiest VMs in AWS or Azure, which will cost you like $900 per month and all, or even more with GPU support, even more, at least $1,000, $2,000, like what we have in our companies for our entire production line. So that is not advisable. So don't try to train. So we use retraining. That's called transfer learning. So basically what CNNs do is CNNs know how to break down the picture. So whatever picture you give, they are actually so generalized that they know how to break it down to a set of features. So what we use CNNs for is basically feature extraction. We are not going to do recognition or classification with that. That is the last dense layer of your network that does it. CNNs don't do classification by themselves. They only extract features from your images. And the very same CNN that is designed to do scene classification can also help you to do segmentation of your textual OCRs and all. Okay, so we use the CNN from SegNet to do OCR. VGGNet to do OCR. And only later on SegNet came. SegNet is basically meant for image segmentation of textual images, but that is a better trained model. So we can use that. So I hope you're able to understand what I'm saying. Most of you have already worked on this. I completely understand. This is not, so you are already having some hands-on experience on this, and you also had some intro into general machine learning. So you know these things. Okay, so just in 5 more minutes, we can actually round up, and I can show you the code also. Just running through, no hands-on. It's not possible to have a hands-on in 1.5 hours, right? To CNNs, just to run that, it will take half an hour. So I already ran it and I have this thing. You can actually use that code and do some experiments with it. So these are the main tools that we use. My personal favorite is Keras. You don't have to directly use TensorFlow directly. Keras and PyTorch uses TensorFlow in the backend. Okay, you just have to install TensorFlow and then you install Keras on top. And Keras is very straightforward. just it's functional. It's very easy. PyTorch is object oriented slightly. You have to create that CNN class and all that. And it's a kind of tedious thing. So I've worked with all these frameworks. I'm more acclimatized to Keras for deep learning purposes. I always use Keras. So I have got the code in both. You can see how it is working. So pre-trained models, as I said, I'm repeating, are the most powerful tools. If you want to do any kind of image classification, use some standard model, SegNet, ImageNet, or maybe VGG16 is a good one. I think it is obsolete because see, it's been some time since I left this kind of core image processing. I don't work on it anymore. I do solutions on images, but the actual hands-on is done by a lot of other core data scientists who are into this. Coding is done by them. I do have a lot of people and interns too. A lot of interns. They like to do this hands-on stuff. They are updated. I'm not onto the actual API side. Okay. So case study explorations that you can do. These are some of the standard projects. Aviation baggage scanner, as I told you. Image tumor detection in medical imaging. It's a very powerful thing. And I do have a paper on COVID detection from X-ray images. That is gathering some this thing. So yeah, these are some of the things that. Just a moment. Can you see my screen and my face?
Your face is not visible till the.
But I turn on my camera. I don't know. I thought, okay, 1 minute. Oh, camera is off, but
Yeah, now it's
Now it's okay.
okay. Because I don't know. It was showing the camera, but the camera was not on. Okay, so this is basically our presentation. Just 2 more minutes, we can just cover the this thing. So I'm just going to share my this thing. Let me check. Yeah. So the slides are there. It is over. So I will just share my Colab notebooks. Okay. Okay, so I'll just reconnect. I don't intend to run them. So what I have is I have a basic CNN forward pass from scratch. So you can just see how the parameters are. You can play around with this code. That is why I made this code in the first place. You can see how the strides are, the formula and all are already verified. You can actually paste this in ChatGPT and then it gives you an explanation of what this code actually means. Or you can actually, if you're a code maverick, you can actually go through. I've tried to give necessary comments. I didn't have much time to do this. This is actually one of my old code. I have to convert that into Python. Yeah, it was old Scala code we used to when we started off in like 2013, 14. The first thing we did was we actually coded CNNs and LSTMs by hand so that the students can actually understand it kind of at that level. At that time, that was significant. Nowadays, nobody cares. I don't think that even needs to be put in the syllabus. But at least as teachers, we can actually go look and understand, satisfy our own curiosity. Our understanding improves, and then your application will also improve. How this exact process and how under the hood these CNNs are programs. This is completely from scratch. This is just the forward pass. That's why I told you this is kind of it's very this thing. So this is a full CNN. So what I did was CNN complete code is there. Part of this code I had ChatGPT generated. I only had the CNN implementation. So I gave the implementation, asked ChatGPT to actually use it and process data. So it actually downloads this JIT train images. These are MNIST images. MNIST you already know, they're handwritten image database. So you have images of numbers which are written by a hand, like around 200 to 400 numbers per set, like 1 to 9, 0 to 9, and then you can classify them. It's a multi-class problem. So you see 91% accuracy, because this is one among the most classifiable data sets out there. You can actually get up to 99% accuracy. So using Keras, I was able to get almost 99% accuracy with just 8 epochs. Very, very accurate data set. So I also have the PyTorch version here. So this is kind of, you can see the numbers here too. So actually it predicted 7. You can see that prediction is 7. Then 2 came, 1. The predictions are so accurate. You can see the actual data too. You see? So initially I was scared because I just put this to run just before the class. So initially it was coming as junk like this, that code had some issue. But then last minute, I think this assistant, I used this Google Assistant, the Gemini Assistant to fix it. Luckily, it got fixed. So I'm happy to see the numbers here. So you can actually see the prediction and the actual value. Yeah. So I think this summarizes everything. So we can have like 5 minutes, 5 to 10 minutes of questioning. Any doubts? And we can also go back to our original question in the beginning.
Thank you, Dr. Vijay. Let me ask a question.
Yeah.
This is PyTorch, Keras are all different kinds of implementations of this PNN, right? As far as I understand, or am I wrong?
They are all different implementations of CNN. That is correct.
Yeah, so uh, for the semis database, the Keras implementation gives some sort of accuracy, and the PyTorch implementation that gives something else. So, what exactly is the reason behind that? Like, is the underlying algorithm also different, or what?
No, algorithm is the same, sir. There's no difference in the algorithm. Implementations are different. I agree. But here, I think even the implementation is the same, because both PyTorch and Keras are using, TensorFlow as the backend. So most of these frameworks, they have this ability to actually call the backend, a separate backend implementation, so that there is consistency. So when you run the same thing, so if it is a TensorFlow implementation, then there will not be much difference, right? And TensorFlow is very much accelerated. The actual implementation of TensorFlow is in C++. So it is native. It is running native. Very quick execution, but the actual implementations done by PyTorch and Keras, they do have their own implementations. If TensorFlow is not available, they probably will switch over to their implementation. That is a Python implementation. That will be slower. Slight variations in training. Even if you train the same data multiple times in the same thing using Keras itself, the same architecture, again, sometimes, if you train it in Colab or train it in your local machine, there will be difference in accuracies, because it is a non-deterministic thing. That accuracy, the number of epochs, eventually it is able to convert. It is stochastic. I will not. That training process is kind of stochastic. So depending on the number of epochs, that might change. Okay, slight variations. But if you train it enough, if that data set is good, eventually all the implementations will give you almost the same accuracy.
Okay.
Yeah. Yes. So I'm just going through the comments for the original question. ML manual feature extraction, automatic feature extraction. Yes. Anyone else who said how they handle feature engineering? ML manual feature engineering, automatic feature engineering. Okay. Okay. So manual feature engineering is okay. We know it is human handmade features. We choose the features. So any example of this in image processing? Anyone working on image processing can mention 1 or 2 manual feature extraction algorithms used in image processing, or maybe signal processing. in speech we have something like that. My colleague Dr. Govind used to work a lot on speech. He's now in KL University. So I came to understand from him a lot of things about speech. So I've seen him work with all these MFCC coefficients. That is basically a hand engineered, it's basically an algorithm for hand engineered features of speechlets, signals. And I think in image we have something called SIFT, scale invariant transform, right? SIFT, scale invariant feature transform. That is also a set of manual features based on pixel neighborhood and all that. These are manual features. Automatic feature extraction. Yes. Pyrodynamics. Okay, great. Yes. Nisha Varghese. Yes. Your answers are on the head of the day. So is Vijay Rajendra. Madam, your answer is also very accurate. So it's basically feature engineering. But the thing is, I also ask a counter question. How do you automate feature engineering? Automatic feature is fine. So that we actually discussed in today's session too, right? What is the automation in feature engineering? See, I don't know whether you've seen that interview. It was a very nightmarish kind of interview because Jeffrey Hinton, regarded as the father of deep learning, probably is the father of AI too, modern AI. He got a Nobel Prize in physics for AI for the first time. No computer scientist has ever got a Nobel Prize. Usually, maybe Turing Award, that is equivalent to a Nobel Prize in computer science. But Jeffrey Hinton got a Nobel Prize in physics last year. For what? For his work on deep learning, for finding the physics to actually start an entire era of machine learning. His contribution to machine learning. This is automated feature engineering. And how is it automated? So he was asked, see, if we build AI, why are you so scared of it? He made a statement that actually made people really, really worried, including me as a AI practitioner. He said, we don't know. We might be heading for a dystopian future. This is not, I'm not quoting him. This is what I understood this thing. He said it's a dystopian future. Why? So he said, see, we don't understand AI. So then the interviewer directly asked him, sir, we made all the stuff, we made AI. We teach it. He said, no, we don't. All we made are learning algorithms. And it is learning by its own accord. So that is what makes me worried. Okay. So we don't know what it is learning, because there can't be anything more disastrous than human experiences to learn from. There can't be anything more disastrous. So human experiences are a bag of mixed emotions. We don't know what it is learning, what it is focusing, what it prioritizes. Everything is automated because we exactly don't know what is happening. Same case with the explainability argument that I put forth earlier. Yes. So this is kind of a balance. So at least now we can be sure that AI hasn't matured to that level, but it is growing very fast. So with the advent of LLMs, we use agents now in the company. We don't use CNNs, we don't use deep learning, we don't use traditional ML. Of course, small problems we have to, statistics we have to, but most of the AI stuff are handled by an agentic framework. All we need to do is write the prompts for the agent and set the goals, design the agent. That's it. It's all prompt engineering. Of course, you need to understand how it is done. You need to have the agent framework. We use our own framework. We build that. So that is kind of, I don't know. So see, if the complexity of the network reaches anything like 1/10 of the human brain, it's going to show up all the things that a human brain might have. Like this is called emergence. Things which are not actually part of it. You put enough complexity into that system, it will start emerging new properties. Okay. Like if you put enough, one neuron doesn't have anything. Put a pile of neurons together, it might be intelligent to solve certain problems. You put more and more neurons, it might even develop a higher consciousness, what we call as morality, spirituality, all these kind of things. Okay, these are all what we call as emergent properties of neurons, of combinations. In complex networks, this is, if you know, this is one of the things in complex networks, because there are emergent things that we cannot counter. We don't completely understand how it is happening. But it's very interesting. So machines can also have these kind of things. Put enough, make a network that is just a quarter or maybe 1/10 the size of a human brain. It is going to have psychosis, neurosis, everything that we have, fear complex, jealousy. You know how the recently the experiments done by one organization, they actually, through set of prompts, they threatened the AI that they're going to shut it down. The AI did everything possible to stop that shutdown from happening. In fact, it actually contacted the wife of one of these operators and told her a fake story or something. Somehow that got triggered. I don't know how. Probably it posted a call and then talked to her or something. I don't know. It just want him to be there. He said, tomorrow morning I'll come and I'll deactivate you. They were trying to, rigor the AI models for self-preservation. It showed self-preservation. Emergent. Nobody saw this coming, but it is showing. It is very much showing. We don't know. So this is going to be a bumpy ride in the future. Okay, so we'll close this session. So I think 8 o'clock, is it, sir? 8 o'clock?
It's like we have the next session. Nobody started directly, but as we have already crossed that limit. But I think we can take a break for maybe 10 minutes and we can start the next
Okay,
session.
sir. Yeah. So maybe 7:45. Yeah,
Yeah, that's right.
7:45. Done.
So, yeah. Okay. So, thank you. That's 6 minutes for a experience. We
Okay.
started with that question. So, what is the difference between an ML and real machine learning and deep learning? And we got a lot of answers from different past. Then he explained the key examples where deep learning explained the process of activity. Then he moved to loss functions and regularization. That facility shows the visualizations of the PS. And finally, she shows the implementation of PS. And with that, she concluded the session on CS. And the participants please don't go ahead. She continued with the session on RNS and that we will start maybe at the so in the meantime, I think we can play a video on our institution, and that was in fact made by our students. And we had actually